Hello. In the last couple videos, we have discussed about the nozzle and diffusers, and now we are going to move on to the second type of the open system, which is turbines and compressors. Okay, so let's take a look at this picture right here. Turbine. What is a turbine? They said turbine is extracted from the fluid, the energy extracted from fluid to do the useful work. Well, then, however, compressor is a device that used to increase pressure of fluid. Okay, so here is something we want to be very clear from the beginning. Turbine is extract energy from fluid. And because they take energy from fluid, so they generate work out. So they get work out. It does work, right? However, compressor is exactly the opposite. Compressor, you need to require work. Instead of generate work, it's require work in order to increase the mechanical energy of the fluid, right? Or pressure of the fluid, mechanical energy of fluid. So that's exactly opposite. So turbine is generate work. However, compressor is require work come in to increase the mechanical energy of fluid. And if you look at the turbine, do a YouTube video on what turbine look like. They have a device that's showing the power is generated. If you have very superheated vapor coming through these blades, and they're gonna be expanded, and then they're gonna change this thermal energy to this mechanical energy to turn this shaft. And then the shaft is actually gonna be inside your generator inside your magnetic coil, so that's generates electricity. So in that case, when we draw our turbine, we often draw something like this, from small end to a bigger end, because it's going to be extract. When you extract the volume, it expands. So start with, this is going to be the inlet. So we have, this is come in. Then we're going to expand at this bigger end, so that's going to be out. In order to do that, this going to generate the work, so it's going to be work out. So that's our turbine. However, for compressor, it's the opposite. You go from big end to the smaller end. So in order to do that, you have something comes in, that's inlet, and then you go out, it's outlet. In order to do that, you compress, so you require work. You have work come in. Okay, so that's the difference between two of them. Now we're going to look at what would be the specific equation for turbine and compressor, just like how we derived for nozzle and diffuser. So in order to do that, we have to go to our most primitive equations we ever had, right? So for the mass conservation, we have mass flow rate coming. M dot in is equal to M dot out. Okay, and then we also have energy conservation. All the energy comes in is going to be flow rate. It's going to be all the energy going out the flow rate. And we expand this energy equation. We have Q N plus work flow rate, work coming, plus summation of all the inlets, if there were multiple inlets, of mass flow rate, H plus half V squared plus GZ That's going to be equal to the right side, which is a mirror image, except we're going to change everything to work out. Okay. So now let's specific using this turbine and compressor. We have only one inlet and one outlet. So because of that, we can get rid of summation. So the mass conservation equation become m dot 1 equal to m2 dot. That means mass coming in is equal to mass coming out. I'm using 1 for inlet, 2 for outlet. Now let's look at energy conservation. Energy conservation is more humongous, but again, we like to make assumption. What assumption would be reasonable for turbines and a compressor? First one, we say it's well insulated, so there's no heat transfer. And we consider there's no potential energy change. We also consider there's no kinetic energy change. So knowing that, we're going to erase some of the terms. For example, there's no heat transfer. There will be no kinetic energy change. There will be no potential energy change. Also, we can get rid of this summation sign because there's only one inlet and one outlet. So knowing that, we're almost simplified. Now let's thinking about, since compressor and turbine, they are totally two different devices. One require work to increase the mechanical energy of the fluid. Another one for turbine is they extract the energy from superheated vapor and to generate work. They are two different devices. So here that's where we're going to start to branch. We're going to come up with two different equations. One for turbine and one for compressor. So let's think about for turbine, we're talking about its generate work, right? It's turn the shaft. So there will be no work coming. So in this case, this will be 0 if it's turbine, right? So in that situation, what do we have then? We'll have, on the left side equation, we'll have m dot 1 times H1. H1 means the inlet enthalpy. Equals, on the right-hand equation, we'll have work out for the turbine, right? Turbine generate work. Then we also have this term, mass flow rate, and H2. H2 means the outlet enthalpy. So if we are going to make this a little bit neat, we'll have this work out generated by the turbine, the shaft work, is going to be equal to mass flow rate of initial enthalpy minus H2. Makes sense, right? Why H1 minus H2 instead of H2 minus H1? Because H1 is this superheated vapor coming, and those energy gonna be dissipated to change to mechanical energy. So H1 is gonna be greater than H2, and that energy loss is gonna be used to generate the shaft work. Okay. Now let's look at compressor. For compressor, it's a different story. For compressor, we need what? We need energy from beginning. We require work to increase mechanical energy of the fluid. So in that case, we don't have work out for that situation, right? However, we require our work come into the system. So our equation will be for the left hand, we need to require work come in, and inlet mass flow rate times H1 inlet enthalpy. That's left hand equation. Right hand equation, there's no work out for compressor, but only thing left is our mass flow rate coming out times enthalpy leaving out. So make this a little bit better looking. We'll have how much work required for the compressor. Work coming in is going to be equal to M. So here, M2 is equal to M1, right? We're talking about its mass conservation. So it will be just M dot H2 minus H1. Well, I think we can figure out why is 2 minus 1 instead of 1 minus 2, right? For compressor, you require work to increase energy of the fluid. So H2, the final state, gonna be greater than initial because it's increased. So you're going to, how much work required? It's gonna be final minus initial. So knowing that, that will help us to get those equations straight. Okay. So quick recap. So for energy conservation equation for turbine, we'll have this equation. Work out generated by turbine is going to be mass flow rate times H1 minus H2. However, for compressor, it's exactly the opposite. It's going to be H2 minus H1. Okay, so that's all the concepts required for the turbine and compressor. So in the next couple of videos, we'll look at some examples of this. And stay tuned. I'll see you next time.